Start in the sunlit waters of the western Pacific Ocean. Hidden thousands of feet below the waves, the Earth's crust is torn open by a 1,500-mile-long scar known as the Mariana Trench. To see the sheer scale of this drop, imagine placing Mount Everest into the southern end of the trench, a localized depression called the Challenger Deep. The mountain's peak would still sit 7,000 feet underwater. This chasm is the result of subduction. In this geological process, the heavy Pacific plate crashes into and slides beneath the lighter Philippine Sea plate, forcing the ocean floor to buckle downward into a steep V shape. This slow-motion geological collision has been grinding for 50 million years, creating a void so deep and physically hostile that it remains one of the least explored environments in our solar system. In 1875, a British naval expedition aboard the HMS Challenger arrived in the waters southwest of Guam to investigate the seafloor. Lacking modern sonar, the crew relied on a primitive measurement method. They attached lead weights to a hemp rope, feeding it over the side of the ship, waiting for the line to go slack as it hit the bottom. Hour after hour, miles of rope slipped beneath the waves. When the weight finally hit the seafloor, the crew recorded a depth of over 26,000 feet, revealing a void deeper than anything known to 19th century science. That single blind measurement ignited a 150-year engineering race. Scientists were forced to figure out how to keep a human being alive under the massive physical forces required to reach the absolute bottom. Descending into the Challenger Deep is a study in compounding extremes. Within the first 1,000 feet, all sunlight is filtered out, leaving the water pitch black as temperatures drop to near freezing. At the bottom, nearly 7 miles down, the weight of the water generates a pressure 1,000 times higher than at sea level. This equates to 8 tons of physical force pressing against every square inch of a vessel. In 1960, Jacques Piccard and Navy Lieutenant Don Walsh became the first to successfully navigate this drop. They rode inside the Trieste, a heavy, spherical pressure cabin suspended beneath a massive flotation tank filled with gasoline. 2/3 of the way down, the structural strain caused one of their plastic viewing windows to violently crack. They survived the descent, but the damage limited their time on the bottom to barely 20 minutes. Modern engineering faced similar hurdles in 2012. During filmmaker James Cameron's solo dive inside the deep-sea Challenger, the pressure caused a hydraulic fluid leak and disabled the submersible's starboard thrusters. Simply reaching the seafloor intact requires pushing the limits of human materials engineering. Survival depends on hulls that can withstand structural collapse and pilots willing to test them in real time. Once survival was proven possible, the focus shifted to a new challenge: accurately mapping a landscape that is completely hidden from view. Researchers now use 12 kHz multi-beam echo sounders to bounce sound waves off the trench floor. When paired with dual-frequency satellite navigation, this technology allows expeditions to calculate the exact shape and depth of the abyss. This bathymetric map, a chart that illustrates underwater terrain, shows the massive boundary where the Pacific and Philippine sea plates meet. The dark blue horizontal line identifies the steepest part of the drop. Sonar data reveals that the Challenger Deep is formed by 3 staggered troughs and echelon depressions, extending 6 to 10 kilometers long. These deep pools align with tectonic bending. As the Pacific plate drags downward, inherited spreading faults are pulled apart, creating these isolated basins. By analyzing the sound waves returning from these tight depth rings, researchers have identified the easternmost depression as the confirmed deepest point on Earth. Advanced sonar technology has finally allowed us to see the bottom, transforming a black, terrifying abyss into a precise and geologically dynamic landscape. For decades, science assumed that extreme pressure and total darkness made the trench floor completely sterile. It seemed impossible for biology to survive in water that is near freezing and under 8 tons of pressure. But when submersibles finally landed on the soft, gelatinous ooze covering the bottom, their lights revealed a thriving ecosystem. The trench floor is populated by xenophyophores. These are giant single-celled amoebas that build protective exoskeletons out of skeletal remains and ocean debris. Near the sediment, swarms of amphipods survive by digesting fallen organic matter. These small, shrimp-like creatures have evolved specialized wood-eating enzymes that allow them to consume debris that drifts down from the surface. The apex predator of the Mariana Trench is the Haddle snailfish. It has adapted to the lightless environment by losing its sight and developing completely transparent skin. These organisms have evolved biological solutions to the same crushing pressure equations that can easily destroy human-engineered metal. Yet, this remote ecosystem is no longer isolated from human activity. Recent dives into the deepest part of the trench have recovered plastic bags and candy wrappers, resting among the ancient biology of the seafloor. Today, crews continue to lower submersibles, like the limiting factor, into the deep, to study this fragile ecosystem and track how human pollution is impacting the bottom of the world. At 36,000 feet, where the pressure equals 8 tons per square inch, biology has found a way to survive without light or warmth. We continue to return to the Challenger Deep because it remains the final, unlit edge of our own map.